spectrum, bandwidth, those are all about frequencies. So what happened is that after the wave have been amplified, have been modulated, the resultant modulated wave, which is going to be the output of the modulator, will have these frequencies. How do we get these frequencies? That's the question.
No, man. I think I get the question. I just didn't understand the diagram itself.
Okay. So the diagram is just showing you that, hey, listen, after we have done the modulation, and mathematically, I think I started showing you guys that last week, the maths of it. So if you remember the maths of it, what we did, we said that, okay, I think it was right here. We said that, let's say that you have this equation 4-9. So this is the carrier that you have. And what you want to do is to change this carrier, the amplitude of the carrier, with a modulating signal or the information signal. So this is a carrier which has an amplitude, frequency, and in this case, the phase is 0, but it has an amplitude, frequency, and phase, right? That's what a carrier has. It has regular signal.
Yeah.
And then you have the information signal. Right. The information signal. So this is the instantaneous voltage of the carrier wave, meaning that for every instant in t, you get a different value for this, which is why you have the excuse me, a wave looking. That's why I have waves looking like this. And by the way, this is an amplitude modulated wave. But just as an example, at every instant. So this is time versus amplitude. Okay, time on your horizontal, amplitude on your vertical. So every instant in time, the amplitude will change, based on the fact that it's a sinusoidal wave. So sinusoidal wave, so every instant in time, right? So that's what this is representing. And then you have the information that you want the carrier to protect. And the information is also going to have a frequency, a phase, an amplitude, right? So that the information signal, the entire signal is what you're going to use to vary or change only the amplitude of the carrier signal. So if you notice equation 410, it is showing you that. Let me just underline it that you can see. Here we go. So right here is your modulating signal or your information. So it is EM sine 2 pi FM, which is the frequency of the modulating signal, times T. And that is being used to change. All of this is used to change the amplitude of the carrier. So remember, the carrier is this, different color.
Yes, sir. I get that part actually, yes, sir.
Hold on. We're going right to it. And this is for other people. So this is a carrier amplitude, and this is a carrier in terms of its angular characteristic, meaning frequency and phase, right? But because of the fact that I want to impress on you guys that it's only the amplitude that the information signal is changing, that's why we group it like this. Okay? Mathematically, it would not make a difference because what we had initially was EM sine 2 pi FM, right? That is being mixed, has been mixed with a carrier signal. Good? So this is showing you that this is the result of the mixing for amplitude modulation. Okay, only for amplitude modulation. Now, mathematically, and I mentioned this last week, this expression, we spoke at least last week about what M is, which is your modulation index. But remember that? The modulation index. I would say that's one time where you don't want 100%, right? The modulation index, M, is the amplitude of and this is for FM. Sorry, this is for AM. I remember this is specifically for AM, only for AM, because FM, the modulation index is different. So it's EC over, sorry, what am I saying? EM over EC.
So you're not recording?
Oh, let me start. I was waiting for everybody. Let me start. And that's the reason why I came here. Let's go back to here and admit and record. Okay.
Just reaching.
Welcome, man. Welcome. All right. So, as I was saying, we know that the modulation index, which is how much to what depth is the amplitude of the carrier's signal is being affected by the information signal. And this is what the modulation index is. And the modulation index can be expressed in a percentage form, which is called the modulation, a percent modulation. And that's so simple by multiplying this. And I spoke about that this last week. You multiply by the modulation index by 100. Right? For percentage. Oops, 100. Right? So that gives you percent modulation. This is percent. Right? And this is one time because if EC is equal to EM, we talked about this last week. Oh my, EC, EM. My apologies. EM.
Is mostly about her. Well, I think right now the Republicans need to stand by this chain. I think many of them will. She's going to be to represent the future of the party at this rate.
Thank you both very much. I appreciate it. Congressman Dent, Worship, thank you. And I want to bring in now the Governor Jeff Duncan of Georgia. And Lieutenant Governor Duncan, look, you and I have spoken over the past months. You've talked about the need for a GOP 2.0. And yet here we are. Our prophecy state, obviously, is
definitely need to have a bit of.
What do you think about what's going on?
Well, I don't know.
All right, so it's EM over EC gives you a modulation index, and modulation index can be expressed in percentage. But just looking at the expression for modulation index, you realize that EM, by changing the subject of the formula, EM, what would be EM from this expression?
EC time M.
Great. Right, so if that is what EM is, then we can basically have an expression with pretty much EC right through, which is what happens in equation 411. By making EM equals to MEC, we can then write back EM from here as MEC right here. Okay?
Sir.
Yes.
We are highlighted first. We are coming from with the arrow. We can just explain what they are again.
Well, the complete thing is the amplitude modulated wave. That's the expression for the amplitude modulated wave. where you had a carrier. So this, you notice right here, this is the amplitude of the carrier, and this is the frequency of the carrier, or an angular the angular expression for the carrier. That's why I marked both in red. But this now, all of this right here is for the information or the modulating signal, the one that you want to protect. But because of the fact that you're using the modulating signal, all of the modulating signal or the information to modify the amplitude of the carrier, we group it as how we have it right here. Okay? To show that it's just the amplitude of the carrier that the modulating signal is affecting, or being impacted upon, or not necessarily the frequency or the phase. So that's how it is expressed this way. We're saying right now that the modulation index is the degree or the amount of, or the how much the carrier amplitude will be affected by the modulating signal amplitude is what is given as your modulation index, which I wrote over here. So small m equals to m, so em over ec. And that should be, if you ever should be doing this and you're having some challenge because you're getting old numbers, then you know that you're doing something wrong, because it's always em, which is the amplitude, the peak amplitude of the modulating signal or the information signal, over the peak amplitude of the carrier signal. And that's supposed to be a fraction because the carrier amplitude is supposed to be a bigger value, protecting the smaller value of the information signal. So that's why EC will always be larger than EM. So it gives you a fraction. That fraction, if the closer the two numbers are, EM and EC, the closer they are to each other, the less modulation the system will be performing. The less protection, I should say, the system will be doing for the for protecting the information. So as I said before, that's one item you don't want your modulation index, which can be expressed as a percentage. If you multiply this by 100, this is one item you don't want. You don't want 100%, because if 100%, it simply means that EM equals to EC. And if EM equals to EC, EC is not protecting EM. If this ratio is greater than 1, then you know for sure. So if you're getting more than 100%, you know for sure you're not protecting the carrier, the information any at all. The carrier not protected it. All right, so because of the fact that we know this expression, we can then make EM from this expression, EM, the subject of the formula. And if that's the case, we get the expression that EM actually equals to MEC, which is what I'm showing you here. That since we know that EM equals to MEC, we can just write back in this expression in equation 411 that EM is MEC. That's all we have done. And then I mentioned that if that's the case, this is how it is represented. But this is not showing that the wave is modulated as yet. This is not showing how it is represented. The modulated wave means that you're gonna have to this means that you're gonna have to expand this expression as expression of equation 411. By expanding the expression, or before expand the expression, we can simplify this expression by factoring out from here. Again, let me just highlight different color. So from here, we can factor out EC. And we factor out EC, we're gonna have E outside into 1 plus M sine 2 pi f inside. Agree? Which is what happens here. When we factor out EC, we get this expression 1 plus M sine 2 pi f, and the E being factored out, the E becomes come outside, so it becomes this new expression as in equation 412. Now, even before we expand this new expression in 412, one other thing that we can do is show clearly that this part of the expression is clearly your original carrier. Remember I said that that's the carrier wave? And we did that from up here. Notice that this is the same as what is here, this. So in amplitude modulated wave, we can clearly see that there's a carrier and something else. So to know exactly what we have to expand the expression. And this is how we expand the expression using trigger identity, or double angle. So this here times 1 is this. So that's when you do this times that. Obviously, you guys are not primary school, so I don't need to show you all of it. So, but that's how you get this. And then what you have left is this times this part. Now, it is 2 sine wave sine. So it's like sine A, sine B. And sine A, sine B, as somebody expressed before, sine A, sine B equals to a half cos A minus cos B minus a half cos A plus B. Which is why if we choose to use all of this as A, so all of this is A. So sine A. So I can say sine A, and this can be seen as B. So this is sine A, sine B gives us, as I said before, a half cos A minus cos B minus a half cos A plus cos B, which is why we get this expression after expanding this expression in 4.13. Having this expression clearly shows you that the amplitude, instantaneous amplitude modulated wave has 3 main components in it. It has Component 1, so it has this. It has this, all of this, and this. So 3 components. The first one shows you that, hey, even amplitude modulated wave has
Washington State Representative Brad Gilbert has already declared he's running, demonstrating with anti-abortion activists.
it has a carrier wave. Again, if you look at this carefully, you see that this is the original carrier wave. So the amplitude modulated wave has in it the carrier wave plus it's going to have 2 side frequency. You notice, so as if this frequency is FC plus FM, which is FC is the frequency of the carrier, and FM is the frequency of the information signal. Right? And over here, the third component is the same modulus, well, same magnitude rather, but here it is FC minus FM.
But even this supporter acknowledges in a place that remains.
If you look at that, you'll see that there'll be a frequency shifting. Because if in one instance it is FC plus FM, then it means that these frequencies for this part is going to be the frequency for this is going to be above the frequency for the carrier, while the frequency for these or for this is going to be below the carrier because they're taking it to frequency from the carrier. So by doing that, we said that the amplitude modulated wave ends up having 3 components. It has a carrier, the original carrier. Well, I won't write on it because it's there already. It has the original carrier. So this is your original carrier. Plus, it has 2 different frequency bands. Because this is added and it's more than the carrier, we say that this is the upper sideband.
Weeks after January 6th, it was a window that was open. You had Mitch McConnell quietly sending.
And this part, or all of this portion, is going to be your lower sideband. Okay. And if we're supposed to represent this in terms of from a graphical perspective, you can see right here that the amplitudes, you have the amplitude for the carrier, amplitude for the upper sideband, and amplitude for the lower sideband are identical. So we could actually represent this amplitude modulated wave in a voltage spectrum, meaning that you're looking at the voltage. So again, voltage versus frequency. The amplitude for the upper sideband, sorry, the lower sideband is right here. That's the amplitude, agree? Which is a similar amplitude for the lower. This is the upper and this is the lower. Okay? But we said that the upper frequency is FC plus FM.
Primary challenge, saying that she's not apologized for her vote, saying that internally and saying that she'll put
because we know that that is the case. And the lower sideband, which is this one, graphically,
believing that the conference will get behind her. But Aaron, this conference is, as I reported earlier, has been focused exclusively on her and not Marjorie Taylor Greene, but we are learning some more information about what was happening inside the room. Marjorie Taylor Greene addressed her past conspiracy theories, suggesting that they don't reflect who she is. And I'm told that after she spoke, she did receive a round of applause from the members in the room. Some stood up, gave her a standing ovation. I am told there have been defenders of hers also inside the room. So even as there have been main defenders.
And of course, you see that this is below a sideband because it's FC minus FM.
So let me just ask you, what Mona just said there, Ryan, was fascinating, right? So you're in this conference, 3 hours, Liz Cheney, career Republican, as Republican as it gets, a person who is so.
And that's how you present the frequency, because you would know the carrier frequency and the two side frequencies. And that's how you present a plot of the frequency versus voltage.
And I could go on. That's the person who got a standing ovation in the.
Any questions?
We've come full circle since early to mid-January when everyone was looking.
So, sir, in terms of actual waveform,
It's the same as what we showed you before. The waveform will be the same. So we're gonna work some questions and you'll see what's happening where that is concerned. In terms of the waveform.
I mean, the fact though, as Martin reports, that Cheney is willing to be subjected to a vote.
Any other questions?
She's in leadership. She should be a good vote. That suggests she's going to stay fine. Negative partisanship is a hell of a drug, Aaron. You know, this glue that holds the party together, especially Republicans, is
All right.
whatever internal problems you have, the other party is far, far worse. And so when they're going after one of their own, that is a powerful narcotic.
sir, those three different frequencies, they interact to form like a complex wave.
Okay, remember you're mixing two signals together. And the two signals have two frequencies.
Would it be three?
Two signal. Listen, you're mixing two signals together, which have two different frequencies. The result of mixing them using amplitude modulation, it shows that you have three different frequencies: carrier frequency and two sidebands.
Schedule fitter, back fitter, style fitter.
Right? So it's not three frequencies you have. You have two signal, two frequencies, but when they mix, because of the whole mathematics would have pen itself out, you end up having FC plus FM, FC minus FM, and FC. All right, so let's look at example 4-4.3.
I spike it. I'll tell them I'm living neutral, customizing margins. They only pay for what they need. Got it?
Somebody want to read it out and then we see you attempt it. Well, it's worked out for you, but
I'll just start reading it. One input to a conventional AM modulator is a 500 kilohertz carrier with an amplitude of 20 volts. The second input is a 10 kilohertz modulating signal that is of sufficient amplitude to cause a change in the output wave of plus or minus 7.5 volts. Determine A, upper and lower side frequencies, B, modulation coefficient and percent modulation, C, peak amplitude of the modulated carrier and the upper and lower side frequency voltages, And D, maximum and minimum amplitudes of the envelope.
Okay. All right. So from what we learned so far, ladies and gentlemen, we have no problem determining the upper and lower side frequencies right now. Remember the upper side frequency is FC plus the FM. What's FC? What's the value of FC?
500K.
500K. And how about FM?
10K.
10K. So FC plus FM then will give you 510K, right?
Yes.
That's the upper side frequency, upper side band. And the lower side frequency or side band would be FC minus FM, right? Again, what is FC? 500. What is FM?
10.
10. So 500 minus 10 gives you
490.
490. So we know the upper and we know lower side frequencies. Okay. What about the modulation? Based on, again, the information we've been given. What is the modulation coefficient? The same as our modulation index. And then we can find a percentage of that by simply multiplying the result of our modulation index, our coefficient, by 100, right? So, what would be our coefficient of modulation? What is small m? How do we find small m again?
The modulation coefficient is equal to EM over EC. So it would be the the peak voltage for the modulating wave over the voltage of the carrier wave, which in this case EM would be 7.5 and EC would be 20, so it would be 7.5 over 20.
Absolutely. 7.5 over 20. And somebody read that out quickly for me.
And I appreciate your time. So, chilling new details about members of the Proud Boys, members plural, on the day of the insurrection and the planning that led to that. Do you have any doubt that this was a coordinated attack when you see these sorts of things?
7.5 over 20. Nobody yet?
0.375.
0.375. So that's the modulation index or the modulation coefficient. And what's the percent modulation?
37.5.
37.5.
Absolutely. Anybody not following me? Nope. Anybody here not following? All right, so we all got it. So far, so good. Not showing a solution yet, you know. We just want you to work. Okay. So from one of the ladies now, what's the peak amplitude of the modulated carrier and the upper and lower side frequency voltages?
But this is been a persistent threat for years. It is clearly swinging right now. We're seeing.
How do we determine that?
Unfortunately, we don't have the legal structure in this country to take the steps that we need, which is why it's so important for Congress to take up legislation.
Ladies, fall asleep on me?
And then this woman, accused for taking part in the riot, is asking the judge to let her go to Mexico.
So that it's an older gavel that was here today on January 6th. So yeah.
Who's gonna take on this one, Miss Brown or Miss Watson?
I mean, it's pretty stunning, right? That's we don't know. What do you make of this?
Well, I mean, these kind of statements are investigators. Every time these people open their mouths, they recorded and they said things that cause bigger and bigger problems.
All right, so like we're gonna have to leave the ladies. Anyone, gentlemen, want to take it on? How do we find the peak amplitude after modulated? No, this is after the signal has been modulated. How do we find the peak amplitude of the modulated carrier and the upper and lower side frequency voltages?
So I think you would times it by the 0.375.
All right, there's no reason for us to guess. Hold on, there's no reason for us to guess. Because we can go back to the modulated wave. And look at these are the amplitudes, right? This is the amplitude, as I marked here. That's the amplitude of the upper sideband.
Okay.
This is the amplitude of the lower sideband. And this is the amplitude of the carrier, right here.
Yes, sir.
So the question is asking you, so this is the amplitude modulated wave. What are these amplitudes? That's what the question is asking you. Is that the peak amplitude of the modulated carrier and the amplitude or the voltage of the lower and upper side frequency? So we know what the modulation index already is.
So it would be the so it would be the modulation index multiplied by the voltage of what we're working with divided by 2 for the that would be for the sidebands, but for the main one for EC it would be EC times the modulation coefficient.
No. EC, look at it again.
So just EC by itself.
See, EC, right? EC. So EC for the carrier is not changing.
Oh, okay.
Right. Good. So that's how we get this part. And D was asking for the minimum and the maximum amplitude of the envelope. Okay, well, that part I can tell you, but I haven't tell you, but it can figure it out. This is it. This is this is an example of amplitude modulated wave. When a wave has been amplitude modulated, the maximum positive value here. What is seeing this? What color is this?
Yes, sir.
Let me use a different color. So the peak amplitude right here would be EC plus. So this is the envelope now, right? Oops. EC plus EM. EC plus EM right here. What about here?
Wouldn't it be minus EC minus EM?
EC minus EM. EC, this is supposed to be a C, EC minus EM. Okay, what about the peak? What about down the side?
That would be negative EC minus EM.
Excellent. Minus EC minus EM. And how about here?
Now that one would be minus EC plus EM.
Plus EM.
Exactly.
Right.
So that's what the question is asking you for. What about the envelope? The peak value, the values for the envelope. So this is the envelope. Completing is the envelope. So this will be EC minus EC plus EM. Okay. So this is actually gonna give you minus the maximum magnitude. So this is so that's what this gives you. This gives you positive V max. And then this right here would be a positive V min and negative V max. Negative V max right here. Hence, going back to the question, to calculate the maximum and minimum amplitude of the envelope, that should not be a problem. Because we know what the maximum amplitude on both sides are and the minimum amplitude on both sides are. Correct?
Sir, scroll up back there, sir. Right back to the wave that you were at. All right. Where is the minimum V min?
Minimum V min?
On the phone with him once I was typing you, yeah. I'm not sure of his last name. I can.
So let's go again. Here on the positive side is a maximum. So this would be positive V max equal to positive V max. Positive only because it's on the plus side or on the positive side of the wave. There's positive V max. Positive. Sure, that is positive. Here is negative V max. While here, this point is minimum, positive minimum, a positive minimum Vmax, or positive minimum Vmax, and this is negative maximum. See, right here? This is maximum, what? Negative V max, right?
So, hold on, so you're telling me that you have two negative Vmax?
No. All right, this is
the one in the middle up here where you were a while ago. Did you just have
hold on. If you just look at it, you can figure it out. You know? So you agree with me that on the positive outside, at the positive section, right here is a maximum.
Yeah.
Okay. So that's the maximum voltage, but it is positive, right?
Yeah.
Good. Right here is the minimum positive voltage.
Yeah.
Okay. So you tell me about the other half. Right here would be what? Right here. Right there would be what? The maximum V minus, right?
So would that be the minimum V minus?
No, this is a maximum. Sorry. What is this? Is a minimum V minus, and this is a maximum V minus.
Yeah.
All right. So minimum V minus.
Yeah, that's what I'm saying. Because I said that if you says max, there's must be minimum.
But you have to know. Here is minus V max right here.
Yeah.
Here is positive V max.
Yeah.
Here, I didn't write it, but it's minimum.
Minimum V max.
Not only, but here is minimum positive V min, right? Positive, right? And here is
negative V min.
Right. So from this, you can actually find out what was asked of you for this, for the because this would be the envelope of the modulated wave. So it's asking you to find the minimum and maximum amplitude of the envelope. So you can find that easily, the minimum and maximum amplitudes of the envelope. All right, so here's our solutions. A solution. Right. So this is it. So the question didn't finish at all. The question continues. It's a expression. You need to find the expression for the modulated wave. And F, you must draw the output spectrum, which is frequency versus voltage. That's what spectrum means. And the final thing was to sketch the output envelope. So, solution. We did this already. We found the upper and the lower side frequencies. Did we?
Yes, sir.
Right. Good. So it's we found it correctly. We also found the modulation coefficient, which is EM over EC, right? And I found the percent modulation, which is just the modulation index or coefficient times 100. All right. So that was A and B. What was C? C asked us
C was for the peak amplitude of the modulated carrier. and the side frequencies.
Okay.
So basically, sir, the only things we would need are C and D, and put them in the general formula for the modulated wave.
Right. So remember that this is EC at 500. We know the frequency, and this is the voltage for EC. Because remember, we have the three voltages, right? We have this is, remember, EC over 2. What's EC again?
Could you repeat?
This.
Yes, 20.
Yeah, the 20.
All right, so the 20 times 0.375
and then divided by 2.
Divided by 2. Okay? And that, remember I said that you have, for both upper and lower side frequency, their amplitude will be the same. The only what will differ is just the frequency shifting, all right? Okay. The bandwidth that this entire signal will take up is the difference between the upper side frequency and the lower side frequency. So it
which is what we got in A.
Right. So it would be 510 minus 490 to give you the bandwidth that this modulated wave would take or would need minimum to carry it, which would be 20, right? 20 kilohertz. All right. The next thing that was asked, C. What would C ask again? The peak amplitude of the modulated carrier on the upper and lower side frequency.
Yes, so that would be the EC would put in the information wave part, and the peak upper and lower would be what we put for the these bands.
All right, so this is what we calculated already. We have them already right here. Remember 20, and this was 20 times 0.375 over 2. Likewise, this one. Right, the next thing was the maximum and the minimum envelope. So remember I said that the maximum of positive will be EC plus EM, which is 20 plus the 7.5, and you got 27.5. And E min positive will be EC minus EM, which is here, 12.5. They only look at one, they only took one side. But of course, if we're really talking about the envelope, we'll have to talk about second half as well. And I just gave you how you'd get that, which is minus EC minus EM for the maximum, and minus EC plus EAM for the minimum value. The spectrum we talked about already, and the envelope we talked about already, which is here. Any questions in terms of that problem? All right. Excellent.
So could you go back up and finish writing?
You're doing some writing here?
Scroll back down a little bit, sir. All right, sir.
All right. Any questions, ladies and gentlemen? All right. Next thing we want to talk about is the power in the distribution. In the way we just looked at was the amplitude modulated wave. So I want to know what's the power? How does the power is distributed? How is the power distributed in that way?
Power is equal to V squared over R. So yeah, so it will be the EC that we calculated. Would it be the EC that we calculated multiplied by what do you call it again? I don't want to give the wrong thing. Would it, the V RMS value, sir? Squared divided by R.
Okay. All right. There are a couple of things we know. Mathematically, we know that power can be expressed as voltage square over R. Agree?
Yes, sir.
Good. Power could also be expressed as I times V, right?
Yes, sir.
Good. So, if we're going to find the power in the amplitude modulated wave, we have to take the voltage component into consideration, because the voltage of the is the only thing that we have to be catering for. So, power in the carrier, we know the power in the carrier because we do know the carrier voltage already. Now, why do you think we have 0.707 VC, EC squared over R right here? No, we're trying to find the power in the carrier. We know the voltage in the carrier.
Sir, because it is the effective value.
You see, we're not, if we just use the EC, it means that big EC, it means that we'll be taking, finding the power in the carrier at that instant in time and that instant in time only. But we want to find the power in the carrier over a period of time.
Sir, because it is still like because it still has a frequency where it's still fluctuating, you have to find the effect. How do I describe it again? You have to find the effective value of the voltage, which is why you would find the RMS value.
RMS value. It's just like thinking about it. JPS will tell you that their voltage is 120 or 240, right? Or 220, something like that, right? JPS 110 or 220 volts. But ever heard that, right? You guys ever heard that? JPS is at 110 or 220.
Yeah, that's the case, 110, 220.
Right. However, 110 and 220, if you should ever take your meter, ladies and gentlemen, and go to the outlet and measure the voltage at the outlet, you'll never get 110 for a 110 supply or 220 for the 220 supply, because what JPSCO will be sending is not a direct current, but AC current, and what they find is that that current will be changing every interval in time. And the thing is that we do not know our instant the voltage is going to go up, spike to the 110 or 220. So what JPS code generally does is try to get a RMS value, the mean square. So we say, okay, instead of measuring the signal when it goes, so spike or what we do is just generalize the power in the amplitude modulated wave. And that's why we have to take the RMS value. Because the RMS value represents an average voltage in the AM wave. And that's why we take the root, the RMS, which is the 0.707. To find a steady state voltage and not just a peak voltage. You remember EC will just be peak, right? It's that you don't want a peak voltage because you realize that this voltage is going to fluctuate. So you find the RMS value. All right. Now, as you can see, power in the carrier equal to 0.707 times EC, and that's all over R. Okay, everybody comfortable with this? Remember, this is just for the carrier. Everybody comfortable with this expression? We're finding the RMS of the carrier average, right?
Or the two are come.
Okay, because we're doing maths, right? Yes, sir?
Yeah, man,
yeah. 0.707.
Come again?
0.04707 squared.
All right.
You're supposed to get two.
Can I just say something, sir?
Go ahead.
1 divided by root 2 is 0.707.
Yes.
So if you were to square it, it would be 1 over 2 because you would be the square would remove the square root.
Okay. So in all right, let's go for some people again.
You and me, sir.
All right. I want everybody to take a time. Take your calculator if it needs to be. Everybody ready?
Yes, sir.
Okay. We square the stuff them so equation 418. We're taking the RMS value and that's why we have the 0.707. Taking the average value of the voltage. Again, because we want to ensure that the voltage that EC has is correct. Correct in the sense that it's distributing correctly, just like a JPS code. So not distributed necessarily at 10, but mix it to find the average voltage. So that's why we don't want it only at this instant in time to be maximum, but we really want average of it at any instant in time. That's why I take the average voltage like a JPS could go. As I say, if you should take your meter and go to any one of the JPS socket and check, you find that you will not get 110 or 220 or whatever the voltage that's been specified, but you get a little smaller voltage because of this concept. So now that we're here, we find that we're gonna square we're gonna square the 0.707. So we square 0.707, we get a half. So it's a half times EC, whatever value EC is. Now 0.707 squared give you a half. Everybody got that?
Yes, sir. Yes, sir.
So we have on top, I should write it, making sure you see. So for here, the top part here, what we're gonna have is E, after we do this, EC squared, yeah? EC squared all over R.
And 1 over root 2 all squared.
But this, because the fact that 0.707 was squared, that is going to be giving you so that's what this will be giving you. This part of the equation. EC squared over 2, EC squared rather, divided by 2, all divided by R.
So I think if it would be clear if you like put root 2 in brackets beside the R. So
Not necessarily. Not necessarily.
No. Well, you probably see, but I'm saying like if other persons to see it, right? So
Right. All I'm saying is that you square whatever is in here. If you square whatever is here, you get EC squared. If you square 0.707, you get a half. So it is EC squared over a half. That's why you square is to get 0.5. So that's why you get a half. Okay?
sir, I mean that's that, sir.
Square, that's what I say. Everything here says squared. You know? So square this. Square that. 0.7 times 0.7. In other words, I'm going to erase this. Never think that this would be an issue. But anyway.
In other words, when you square it, you don't need
Let's get to grammar school.
You don't need to
All right.
So hold on. So we're gonna have 0.07 squared, yeah, times E EC squared. And then all of that is going to be over R. That's what this is giving us. When you squared 0.707, what do you get?
You get 0.5, in other words, a half.
So, exactly. So what happened is that this now is going to give us
EC squared over a half.
this. This is a half. Half times EC squared. And then all of that is going to be over R. Okay. So that shut that there, I go through this door. So this is gonna be EC.
EC squared divided by 2.
Squared divided by 2, and then all of that is going to be divided by
R.
R. All right, so you see how we get that now? That was the same thing I had up there before now.
The thing is that what I'm going to see is that 0.707 is 1 over root 2. So when you square that, that's why you get 1 over 2. So it'll be 1 over root 2 times 1 over root 2, which is equivalent to a half.
All right, so from what we have on screen here, we know from, again, primary school maths that this would actually end up equal to EC.
Sir, we know some later one under that, sir.
Divide by EC, right? Squared.
Yeah, divide by
Yes, sir. EC squared.
Okay. Now, this part is like saying, again, EC squared over 2, yeah, times invert this, yeah, 1 over R. Because you divided, right? So it's like if you want to make it come up here, you put this, okay, erase this again. So there, right?
Yes, sir.
But so you don't like facts?
No, that's all the lecturers them always do that. We don't know what
No, because at this level,
that's like primary school. I don't know.
It is primary school, because it's primary school that you learn these divisions. So this here, but at least that's what I learned in primary school. I don't know what's happening in primary school these days. So this here is like saying EC squared
Over 2 times 1 over R.
Times, because it's 1 over R. That's what this part equals to. And trust me, I don't know about you guys, but that's what I learned at primary school. We used to have to do things like reason and mental ability and all them things. So we had to not just pick a number, we had to know how to calculate these things. But then, Roy.
Yes, sir.
Good. You see what's going on?
I understand everything in it, sir.
Good.
But it's just that
You
somebody
don't like the term primary school.
Yeah, because now there's why the lecturers them always refer to primary school when they want to.
And I can tell you from my personal experiences, because of the fact that the truth be told is that this is what I did at primary school, and you guys are far brighter than me. So If I did not,
So you think that, sir?
So everything is everything is set in stone now. So I believe
so that's,
everyone's all right now.
that's how we get this expression. All right, EC squared over 2R is the power and for the carrier. Remember, you have three components to the AM wave. You realize we had a carrier and we had two side bands, right?
Yes, sir.
So this part is telling you about the power in a carrier, or we need to find for the total amplitude modulated wave, we need to find this part, which is the power in the carrier, plus we need to find a power in the side bands, right?
And we previously stated before that the voltage peaks in the side bands would be EC times the modulated coefficient divided by 2. So it would be whatever we get for that times 0.707. Square that and then divided by R.
All right. So I like how you say it, sir. But if I say it this way, the students are most of
Yeah, I understand that.
By the way, based on what you just said, everybody's clear. Everybody are you all confused based on what he said just now? Remember what we want to find. All right, just to simplify things, because I want to make things as simple as possible. We need to, for the AM wave, we need to find the total power, how you represent the power, right, in the AM wave, right? So the power in the AM wave would be
power and
it'll be the power in the carrier, yeah?
Yes, sir.
Plus the power in the upper sideband plus the power in the lower sideband.
Question, sir. Wouldn't the power in the upper and lower sidebands be the same?
They would be.
Okay. So,
but we just want to make sure that people are seeing the steps.
Okay, fair enough.
All right. So, in order for us to find the power in the total AM wave, we have to find the power in the carrier, which is what we just did. We found an expression for the power in the carrier because we know that power is voltage squared over R. And the voltage in the carrier is EC. That's the voltage in the carrier. So it'll be EC, yeah, squared over R. But it's not just EC squared over R. Because if we just use EC squared over R, what would be happening, ladies and gentlemen, is that we'll be representing the power at a peak voltage.
And it is unstable.
Right. So what we do is to find the RMS voltage,
which is the average.
Right.
More stable.
Right. Which is why we say that JPS could give you more stable voltage at the little less than the 110 or the 220. Good. So now we have a representation for the power in the carrier. We need to do the same for the power in the upper sideband and the power in the lower sideband, which, from what I said previously, they're the same, right? So how do we find it? Well, it's always important to understand and remember that the power in the sidebands is a function of, or the voltage in the sideband is a function of the voltage in the carrier. Remember, we proved that from before that the expression MEC over 2 is what we can use to represent the voltage in the carrier. Sorry, the voltage in one of the
Sidebands.
right. So again, because of the fact, so we know that this is what we're going to be using to represent the voltage in one of the carrier sideband, and this actually is going to be the same as the voltage in the upper and the lower sideband, right? So what we have to do is to find M. Remember, no, it's power. It's M E C. Yeah, over 2. Yeah, but because we're trying to find the average power, we're gonna have to find 0.75, 0.717, right? Or root 2. That's right, root 2. It's easier. So we're gonna have this now, not only at peak, because if we leave it like this at peak, it's not gonna help us because it's power finding. So we need to also find it. We need to also express RMS value. So how we're gonna express this in terms of its RMS value is to say, okay, let's do this.
Times it by root 2.
We're gonna have remember 0.7707. Yeah, EC times M all over 2. And all of that is going to be and all of that, and sorry, and this, all of this is over R. Because that's what power is. Voltage squared over R, agree? So if we do that, square, so going over this side, again, just to make sure on one page for people seeing. So we know that 0.707 squared is what?
A half.
A half. So 0.707 squared is a half. So we're going to end up, we're left with E C M. If you want, I can put that all squared. So this part is squared. And because I took care of the 0.7 before, we know that that's a half. All right. And then now, all of that is going to be what? All over. Hold on, make sure that I'm doing it right. Okay, so
So wait, sir, to confirm, that 2 that I have, that 2 is representing what?
So the 2 is also, remember now, we're moving from here to here. We squared everything here, so this is going to be a 4, right?
Something else that you're missing.
Come on,
But it
let's
depends on.
work with me. Work with me.
Mhm.
Work with me. So everything here is squared. When we square this, it's gonna give us a half. Yeah? So we can say a half, if you wish. Okay, square already, right? Yeah?
Yes, sir. Just that
Okay.
you also have a quarter somewhere.
Oh, hold on, man. We're working there.
Oh, okay. Just that I thought you forgot it. That's why I mentioned it.
So we take care of 0.707 already. That's a half. Cool. So to make things whatever. this is over. This is the 0.707, so that's a half. Okay, that's squared. So that's left us now with this part. Because remember, we don't square that part as it, right? Remember, we're working from here. We square the 0.707. So we need to square the EC, we need to square the M, we need to square the 2. Agree?
Come on, that's clear, yeah.
Cool. All right. And this is supposed to be a 2. Just making sure that everybody is seeing and following. And then all of that is going to be over. All right. So let's finish map and maths out. This part, no. Oh, and that's not correct either. You guys not following me, you know. You guys not.
What is wrong with it?
Well, I'm gonna show you. So right. So we're gonna end up having all of this times 0.5, agree?
Yeah. Which is times half, yeah.
Right?
But you had there a while ago.
Yeah, that's what it is.
I know. I'm moving it from here.
Okay, fair enough.
Okay.
But you sound like you were doing something wrong, but you had the right thing.
All right. Okay. Let's square this. Let's do the square now of this part. So if we square all what's happening here, we have EC squared. M squared
divided by 4.
And that's going to be divided by 4, yeah? And then all of that is going to be now what? Multiply by
half.
Multiply by half.
And then all of that is being divided.
All of this now is going to be over
R.
All right. So if everybody follow that now, you're supposed to can tell me what's the final expression.
MEC all squared over 8R.
Okay. Are we all there?
Long time.
All right. I find that some people are very quiet today. Me? Me, I teach. All right. So what happened is we have the power. All right, where am I? The power in the upper sideband. So this is where I wanted us to be. So we know the power now in the upper sideband is going to equal to the power in the lower sideband, which is what we just calculated and got this. Agree? That's what we just got. from our calculation. So now we have the three pieces of power that we need. Okay? And by the way, because of the fact that this is equal to that, it means that we can rearrange equation 19, which is this, that the power in the upper sideband equal the power in the lower sideband, which is the same thing here, which is going to equal to what? Just rearranging, just for cosmetics, it's going to be equal, everything on top is the same, see? Everything on top is the same, m squared, EC squared. But here, what I did is to rearrange this as 4 times 2r. But you see that? It's the same thing. This and this equation is the same. Now, why is it that we wrote this as like this and not leave it like this? And about
Because now we get back the previous format that we used to find the power for the carrier.
Exactly. Because we know that this, based on what we did our calculation before, this is what? The power in the
carrier.
This actually is a power in the carrier. So now we can write it that this actually, this power in the sideband equals to pretty much a quarter of the power in the carrier, right? So we said we know that this is actually PC because we did that calculation already. So therefore, we can rewrite this expression as this. Equation 421. So instead of writing back EC squared over R over 2R, we can say that this is actually PC. So the power in the sidebands equal to m squared over 4 times PC. So everybody up to now should have this locked. Which means if we're writing the total power in the AM wave, the total power in the AM wave equals to the power in the carrier, which we know as EC squared over 2R, plus the power in the upper sideband, which is m squared PC over 4, plus the Z, which is why the power in an AM wave can be written as this, but it's not. Well, of course, we can simplify this expression because you realize we have a lot of in the three pieces we have. We can factor PC, right? Because we have PC. So factoring PC out of this expression, and what I did was done first. Again, I'm not going to say it, Mr.
Stuart.
No, Mr. Delroy. Now I'm going to say primary, but it's because these two are the same. Finding the LCM gives you this. Make sense? These two are the same. Finding the LCM gives you this. So we have this and this actually is going to give us that. By simplifying the LCM and doing our necessary from LCM, which shouldn't be that difficult. Excuse me. So from this now, we can actually factor out PC. So factor PC out, and get the power in the carrier equals to 1, PC into 1 plus m squared over 2. And this is the proof of how you get the power in an AM wave. We don't even need the carrier expression anymore in terms of voltage. All we need is just to know that PC, and we can say that total power equal to 1 plus m squared over 2. Any questions? Chad, you're still with us?
Yes, sir, I'm here, but in and out.
In and out. All right, I want to do more in than out, boss, you know? We don't want to lose. I was talking to the ladies, asked the ladies to help me out with something, and they disappeared on me, so I'm assuming that Miss Brown and Miss Watson are no longer with us.
Make it sound like them dead, sir.
Sir, I'm here, but I'm having some internet issues, so I'm in and out sometimes.
Same with me. That and the current situation that I'm in, environment. But I'm still listening though, sir.
Okay, let's stop it to know that you're serious. I hope you're following so far. So now we know the power, we know the voltage, and an AM wave. If you're given example 4, we should then be able to solve the problem. What happened to Mr. Hope today? Hope to didn't join us today. Sir William, so, let's read to the question and see if we can start us up with the solution, the first part of this question. Travis?
You want to know some read through the slide them already? I could remember the answer right now. Make no sense.
You know the answers?
Yeah, man.
Alright.
So, when I actually read through notes, I'm very quiet in a class. Very, very bored.
And when you that might be true. And sometimes when you're very quiet in class, in-person class, you're actually asleep. So
but I'm from prep school, so
so just want to make sure is that you're not going from one extreme to the next with us,
Yeah, man, you understand. So
all right, so pretty much the question is asking us to utilize the information that we have garnered so far in order to solve this question. So we know what a DSBFC is. It's a double sideband full carrier. Double sideband full carrier AM wave. And it has a carrier voltage of 10 volts. It has a load resistor that's going to pass before it transmits. of 10 ohms, and it has a modulation index or modulation coefficient of 1. M equals to 1. What do we say about a modulation index of 1?
It is not really modulating.
Okay. Well, it's modulating, but it's not it's not doing what
it's not protecting. Yeah.
Right. So it's not really protecting the signal. So anyway, we have that, and they ask us to determine the power of the carrier and the upper side bands. So in other words, what's the power of the AM wave? So we're gonna have to find the power of the AM wave. We can do it using one simple equation, or we can do it going through all of this, what we just went through. We went through all of that to prove that the power the overall power we could find it's not asked here, but we could find the overall power PT of the AM wave as simple one plus m squared. M squared over. Forget already? 2.
That would have to be multiplied by PC as well, sir.
Times PC. Yeah, sorry? Times PC. Okay. Well, what is PC? Based on what?
EC squared over 2R.
BC is EC squared. I will know EC because EC is VC, right?
Yes, sir.
EC squared. Squared over 2R. 2 times R. And we're given what R is. We're given what, and this is supposed to be an equal sign. We're given what R is, and this is not alpha, it's actually 2.
You know, sir, don't worry.
So we're given what EC is, we're given what R is, so we could find PC. Finding PC, we know what the modulation index is, in this case it's 1, so we could find a total power. Right, this way, the short way. So somebody work with me now, and let's use this, and then we're gonna use the way how it is done, and in the problem, and see if we come to the same thing. So, EC squared. So that's 100 over 2 times R, which is 20. 100 over 20 is what?
5.
So PC is gonna be 5. So it's gonna be, so the total power is gonna be 1 plus, what's the modulation index? It's 1.
1.
So it's 1 plus a half. Yes? 1.5 times 5.
That sounds like 7.5.
7.5. So our total power in this AM wave will be 7.5 watts. The other way, as per the question, is that we could find the power in a carrier plus the power in the 2 sidebands. We know what the power in the carrier is already. We saw that was 5. We did that already. What about the power in the sidebands? The power in the sidebands is m squared times PC over 4, or m squared times EC squared over 2 over 8R. So we could do that one way or the other. We will come to the answers for upper sideband, lower sideband. Okay? And if we know the power in the upper sideband and the lower sideband, then we could actually write the expression as, again, the power in the carrier, total power in the carrier is going to be PC plus P lower sideband plus P upper sideband. And if you know PC as 5, the power in each of the sideband is 1.525. So the total is going to be 5 plus 1.25 plus 1.25, which works out back to your same 7.5 watt.
Just wanted to make sure I heard it correctly. Because it sounded as if you said the power in the total power in the carrier is equal to that, but to be the total power of the yeah, okay. Just I thought you said carrier wave. Don't worry.
Okay. So whichever method you choose, you would see that it comes back to the same thing. See, eventually they worked it out. And that was a part of what was asked eventually in the question. Power, total power in the modulated wave. The power spectrum, a picture of the power spectrum looks like this, as you can see. The power versus the frequencies. So carrier frequency power, a lot. 5 watts, and the power in the lower sideband and the upper sideband is 1.5 watt each. Now, ladies and gentlemen, this is where we're gonna look and wrap. You remember a week or so ago, we said that we're transmitting the signal, the modulated signal. If we transmit the modulated signal, AM modulated signal, as is, we'll be sending from transmitter to receiver 3 things. 1, we'll be sending the carrier as well as the 2 sidebands. Do you recall that?
Yes, sir.
However, as I alluded to, the parents taking the child to school, the parent has reached with the child. The purpose is the child getting or grabbing or obtaining an education. Do you still need a parent?
No, sir.
At the school?
No, sir.
Good. So one of the things that is usually done is that you remove the carrier to make the system more efficient. Make sense? Move the carrier, right? Because there's no information in the carrier. The carrier is a carrier. And left with the 2 side bands or side frequencies now. And one other thing that I said is that the side frequencies are carry the same information. It carries the message signal that has been modulated. But if we transmit both the carrier and the 2 sidebands, what I mean is that the power that will be required to transmit the information would be a quarter the power is needed. You realize that? Because you'll be taking away the carrier, the power in the carrier. And you realize the power in the carrier. Just look at our graph based on what we calculated. The power in this example, the power is 5 watts. So in other words, we're using all of 5 watts without the necessity to carry, to use it, right? We don't need it because now the sidebands have the same information. So if we get rid of one of the sideband as well, we're only left with just one side frequency, right? And how much power would we be? And the one sideband does have the information already, but we'll be also saving because we'll be thinking about using less power to transmit the same information that we're desirous of, right? So it's always best when we're transmitting an AM wave, or when we're about to transmit an AM wave, remove the carrier because it serves no purpose. It has no more information. So move the sidebands and the carrier frequency. And what is left is a single sideband transmission. Only single sideband will transmit. Any questions?
Hello, sir.
Yes.
Yeah, I was wondering, like the radio stations, this will be something they consider, how to broadcast and deliver whatever content they want, so desire.
It is absolutely, because there are a couple of things in the telecom industry that are critical. One of them is power. There's not a direct correlation between power and expenditure.
Yes, because based on the nature of my job and everything, I encounter where the power and the modulation is a huge factor and may cause interference.
Right. So what they try to do is to use some form of filter network to remove the carrier. And if you remove the carrier and they remove the one of the sideband and left with only one of the sideband, you still be surviving because you still would have the information in that one sideband.
Okay.
So yes, they do eliminate the carrier. Because of the fact that they will be paying a lot more to Spectrum if they were using the power, right?
Yeah, that might be a factor based on. Pardon me?
I said it is definitely the case in the real world, in the practical world. You have.
Yeah, I know what you're talking about. Right. Where they have to pay for frequency license and broadcast license.
Absolutely.
So I know that is like pretty costly, and then the area of which you want to be and what you want to cover is a huge factor as well.
Absolutely.
So like, there's a question. Maybe I can email it to you and so forth, because I'm kind of in a situation where like an interference and so forth. But there's some things I need to clear about chunking system and chunking radio system.
Right.
Yeah, so it's just like something that I encountered this week where I need some clarity.
Sir.
Any other questions? Any other concerns? Because we're gonna leave it
Question.
Go
Is
ahead.
there any disadvantage to single band um transmission?
Brilliant question. We're gonna look at single sideband transmission. I said, but actually, there's not much in terms of disadvantage. The biggest problem is the complication of the receiver to as compared to the regular AM, because it has to now look for the specific. It has to read the single sideband receiver will have to generate frequencies similar to the carrier, and then it has to remove the carrier and try to remove that mixed signal with the carrier. And you know, to remove it, because remember you transmit something without carrier in it. Remember that, right? So you mix it, you have the AM wave before you transmit it, you take out the carrier and transmit. The receiver end, before it can actually accept that, well, listen, I have received the transmitted signal. It has to do its own thing. It has to do mix a signal again and receive it and by putting in a carrier and then filter it out. So because of that, the equipment itself that is required at receiving end is a little bit more complex than the ordinary AM wave.
All right, folks.
All right.
So, sir, at the receiver, would there, considering the fact that based on the examples, the carrier frequency would typically be a higher frequency than the information frequency, sir. Would it be a case where they use a low pass filter to filter out the carrier wave, or it would be more complex than that?
All right. So before you filter anything at the receiving end, it has to mix. Because remember, you transmitted the signal without a carrier.
Mm-hmm.
How is it that the receiver is going to pick up your signal? And because remember, it needs to get the signal perfect. So it has to filter on a particular frequency to get the signal. So yes, you mix it and filter it out. You mix it and give it in with a carrier, same carrier, to get the same frequencies, but you're gonna actually filter.
Right, noted.
The carrier and one of the sideband.
I'm sorry, in relation to what you were saying earlier, that one of the frequency band is quite adequate to carry the signal, and in doing so, the system uses less power.
Yes.
If that's the case, then why would be the purpose then to have both up and lower bands in the first place?
The purpose, you ask what's the purpose? And I'm interpreting that to mean if you can transmit without a carrier, why you need to do the modulation to put a carrier on it? That's what you're asking?
I'm just saying that if one of them is adequate enough to carry the signal, why consider both of them to carry the signal in the first place when it would want to result in using more power?
Oh, I think I understand this question, sir. Hold on 1 minute. Basically, his question is, why would people use the double-sided band suppressor carrier versus the single band?
Okay. Well, if that's a question, Mr. Delroy.
Yeah.
Well, because each has their own advantages and disadvantages. It could be a case where, with a double sideband, just as an example, if you lose or if the information get corrupt on one sideband, it doesn't necessarily mean that it is corrupt on the other side. And what you can think about right away is that if you transmit double sideband, if something goes wrong with one of the side of the, let's say, upper sideband, you still have the lower sideband to it's a redundant sideband then, eh? So some people use that as one of the advantages of using
both bands.
Both sides, yeah. As compared
so the only disadvantage is that it uses more power.
Don't quote me and say that's the only disadvantage. We say we're going to do a whole chapter on that.
I'm not saying that's the only disadvantage. But,
right. Yes. If you say one of the main disadvantage is, yes, that is it. All right. If there are no more questions, we're going to leave it for tonight there. I see where you guys are locking in and getting engaged. We're going to wrap up next time looking at the current in an AM wave. And then we're going to be starting looking at FM wave. Okay? So you have the info. You can go ahead and start doing your reading. Nothing is stopping you.
Right then. Good night, sir.
All right. So good night, everyone, and thanks for stopping in. We will talk, God's willing, next week. Remember what I said we're going to be looking at, so you can please continue your watching and reading in order to try and keep yourself abreast with everything. All right.
So yes. The video is posted. Where the video is posted?
Your colleagues can answer that.
Isn't there a YouTube thing or something like that?
It is. But it was posted in the group.
Oh, sorry. Well, each recording posted in the group. Just looking at a group.
Yes, in the group. So you can just check back, and then if you miss a link, you can ask back for it, if anything.
All right. Thanks so much.
Yeah, man.
All right, as I say, good night again, everyone, and stay safe. Remember to try to protect yourself as best as you can, all right?
Yes, sir, you too.
All right.